Hi, welcome back. In my previous video, we looked at two functions, sine of x, and we had that polynomial function, x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. And we used it to say how we can use this polynomial function to better approximate sine of x because it tends to follow the curve more than a standard tangent line. In this video, we're going to talk about what that function is called, that polynomial is called. Our function, this polynomial that we use, is something that we call a Taylor polynomial. And much like the tangent line, we use it to estimate the value of a function. But it is far more accurate as long as within a certain interval. You might remember in the previous video, if we went past the x equals 3, it diverged and it wasn't very useful for us. So we'll talk more about that level of certainty, that interval of certainty, a little bit later on. But right now, we're going to spend time generating what we call a Taylor polynomial. So let's look at how we generate this. Now, I have another video that you can click onto that talks about the math behind this. And please definitely take a look at that video. It's fascinating. Smash that like button. So, just like a tangent line, we're going to use derivatives. Now, we have to pick a known starting value. In this case, because we're using sine of x, we're going to use 0 because I know what the sine of 0 is equal to. Now, it also just happens to make sense. Uh, when we let x equal 0, it's a very special Taylor polynomial called a Maclaurin polynomial. Maclaurin was another British mathematician, I believe he was Scottish. Check me on that one. Uh, who also used polynomials to approximate values, but he said if we start at 0. So a Maclaurin is when we start at let x equal 0. Maclaurin is a Taylor polynomial starting at 0. That's it. And again, this is our known value. So we're just going to take a bunch of derivatives, and we'll talk about why we do this in just a moment. Now, the first thing we're going to do, we want to find the nth derivative. That's what this little n means here. We want to find the nth derivative. So the 0th derivative, well, that's just the original function. That's sine of x. To get the first derivative, that's just going to be cosine of x. The second derivative is negative sine of x. The third derivative, negative cosine of x. And the fourth derivative is sine of x. And then the fifth derivative is cosine of x. I'm just taking derivatives. Now, just like a tangent line, we're going to find the values of those slope at those. Now, we sometimes call 0, this is the center. And we're just going to find the value at that point. We are going to find the value of the derivative, not at the derivative, of the derivative at that point. And we call this a center. And why do we call it the center? Again, if we look up here at x equals 0 is where we are centered. All right, so let's find their values. The first one we're going to take a look at is the sine of 0. Well, that's just 0. The cosine of 0, that's 1. Take the derivative at 2, I get negative sine of 0, the second derivative at 0, sorry, and that becomes 0. The value of the third derivative becomes negative cosine of 0, which is negative 1. And we got the fourth derivative, which is just going to be sine of 0, which is again 0. And the fifth derivative, which is going to be the cosine of 0, which is going to be 1. Yes, there's kind of a pattern here. So next, once we get this, what we've just generated is the coefficients. And what these do, these are going to help us generate the coefficients. And that's what we use that for. So let's take a look at what we do here. Here's how we generate our Taylor polynomial. And it says this: the nth order of a Taylor polynomial centered at x equals a, they have to tell you where it's centered at, is the following. We use the phrase p sub n of x. P for polynomial. Sometimes you'll see this, or we'll see Tn of x as a Taylor polynomial. I am going to use P sub n because that's how I roll. Notice right here, it's going to be the value of the function plus the derivative times x minus our center. A is the center. Now, also notice, if you look only at the first two, that's your tangent line. You can verify that. If I bring the a over, this is really saying this is going to be, if I bring this f of a over, it's y minus y1. That's just my tangent line. So we, even in Taylor, we do see our tangent line polynomial, but then it gets a little bit wonky. We're going to add, notice here, the second derivative at a divided by 2 factorial. Yes, there's a pattern. Times x minus a squared plus dot 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 plus, and now we come to the crux of it. This right here. This is what we want. This is what we call the Taylor polynomial. That's our Taylor, and we're just going to memorize it. And what it says is we are going to find the value of the nth derivative at a divided by n factorial multiplied by x minus a to the n. Now, again, where does this formula come from? I show this in another video. I'll try to I'll try to put the link there if I can. And we're going to add all of them up. And that's what this says right here. We're going to add them all up. This is a summation of a series, And you might remember from pre-cal last year, a series, we just add a bunch of terms. We just add a bunch of terms. Now, so the degree n of a polynomial, and here's how, so let's take a look at how we can generate this. So what all this right here says right here is just that a is the center. And in this case, our center is 0. So to draw your Taylor polynomial, here's what we're going to do. Now, for us, when we look at this fn of x, be very careful. I almost forgot this. This is the value of the nth derivative. If you look at our example up here, we took 5 derivatives. So for us, n will be 5. So to generate our Taylor, we would write this as a what's called a fifth degree Taylor polynomial. And we're just going to follow our rules. Equals, we're going to start with n equals 0. And I just plug it in. If n equals 0, I want to find the value of the nth derivative at 0. And if we look up here, it was just 0. I can just put 0. So plus 0. Plus, now I'm going to do n equals 1. Well, my rule says now I'm going to find the value of the first derivative at 0. And we said that was equal to 1. So this is going to become 1 over n factorial. I'm using my rule over n factorial. And I'm going to put that over 1 factorial. I'm not worried about simplifying right now. And that's going to give me x minus, ready? What's a? Well, a is my center. And we said that the center, excuse me, we're going away, was 0. And that's going to be to the nth power. So I put a 1 up there. Next, let n be 2. And the value of the second derivative we said was 0. So that's just the whole term just becomes 0 there. And then plus, now we got to find the value of the third derivative because now we're on n equals 3. And for n equals 3, the value of the third derivative we said was -1. This becomes over 3 factorial x minus 0 cubed. You see the pattern. Next, do n equals 4. Well, the value of the fourth derivative, if you look above, was also 0. And then to do n equals 5 plus, well, the value of our fifth derivative up top, we said was 1. And that's going to give me 1 over 5 factorial x minus 0 to the fifth. And this is what we call our fifth degree Taylor polynomial. And we could rewrite it by simplifying it. 1 factorial is just 1. This just becomes just 1x minus 1 over 3 factorial. Whoops, sorry. 1 over 3 factorial. Now that's just 6, by the way. We'll talk about that later on, okay? X cubed, the n to the 4 and 4th, n equals 4 is just 0, so I go straight to the fifth, and I get a plus 1 over 5 x to the fifth. And notice, this is exactly that polynomial we got for our sine curve. And what we say is that this approximates the sine of x near x equals 0. And now I can actually use this. So, ready? See if you can solve the following. Try it out. What would be the integral from 0 to 1 of sine x squared dx? We'll come back and try that one, okay? All right. I hope you enjoyed the video. And in my next video, we can go over a few of the homework problems together, okay? I'll see you then. Bye-bye.